the genesis of this talk was a couple years ago. We do an annual event for the industry. We call it PE Showcase. So we decided to educate folks on the various technical notes and technical reports published by the Plastics Pipe Institute. They don't just handle polyethylene at PPI, they handle other materials as well, but their primary mission is to work on polyethylene in its various forms in a variety of industries. And the one we care most about at the PE Alliance is the Municipal and Industrial Division. Could you go to the next slide, please, Matt? That book that Drew referenced is this book that's published by PPI. So this oftentimes is the first exposure people have to PPI that are using it in the municipal marketplace. Great resource. And as Drew said, we can send it to you for free. It's a PDF. The great thing about the PDF is you can search by word or topic, whereas in the book, you've got to go through the old way of using the index. But the key people behind the PPI, the Plastics Pipe Institute, next slide, are David Fink and Camille Rubiez. So these guys are running the show as it relates to water. David Fink is CEO of PPI. He came out of WL Plastics a couple of years ago. He's an engineer, has a wonderful command of plastics as it relates to piping materials. And Camille Rubiez has been doing this for years. So he's head of the Municipal and Industrial Division. So he has personally authored or overseen a lot of the documents that we have today. And we wouldn't be able to talk about a lot of the stuff we talk about here at the PE Alliance if it weren't for these two gentlemen and the volunteers from the industry that work on the various committees that publish these documents. So our hat goes off to these guys. Matt, I'm going to turn this over to you, and thank you very much, speakers, for doing this for us at the PE Alliance today.
All right, thank you, Peter. So just real quickly introducing myself. So I work for Performance Pipe, and I'm in our technical service engineering group. I've been in it for going on 4 years, and my day-to-day life is answering questions to kind of point people to the resources that they need for their cases. So a lot of the content of this entire presentation. So back to the literature. There's more resources, lots more. So we've got pipe calculators that help determine DR for based on pressure, flow, burial, comparisons between different pipe materials, designing HDD operations and other pull-in applications. There's installation guides and case studies that help you design the difficult tasks that you require. The PE piping industry, it really wants people to use PE piping or HDPE pipe. So we're really going to go out of our way to produce the guides and the literature that help you accomplish those projects. So the PE industry, we don't shy away from those difficult tasks. You probably already heard it in the intro video, like HDD or pipe bursting. We want the hardest projects you have, because we can prove ourselves in those environments. You're not going to have any question about taking it to the rest of your system and modernizing it. So in this presentation, we hope to arm you with the knowledge of some of the best resources for managing the whole pipe life cycle. So that's going from specification into design, installation, and maintenance. So these handpicked resources are supposed to be used in concert with these other more general topics, such as, general guides rather, like the PPI handbook of PE pipe or the PPI PE piping systems field manual for municipal water applications. So without further ado, let's jump on into it. The first pair of literature we're going to talk about has the point of building confidence in HDPE itself as the pressure piping system of choice. So TR3 and TR4, published by the PPI, are a key resource in identifying the materials that are going to be suitable for the long-term stresses that you would see as a pressure pipe. So TR3 is a more detailed document outlining the stringent testing requirements and the process that we use to certify certain plastics, which include like PVC, PEX, HDPE, and polyamides for pressure piping applications. And then TR4 is the more practical document because it's a listing for resin products that have been proven to meet that high grade of quality and manufacturability to meet the requirements of TR3. So in TR3, hydrostatic testing is performed on a whole bunch of pipe samples that are going to be conditioned to temperatures higher than normal operating conditions for over 10,000 hours in an array of incremental stress levels, those stress levels being way higher than what you would ever expect in a real pressurized situation. And so on this chart, you'll see each of the X's, they kind of indicate a ductile failure point. So these data points, they're used then to draw a more highly confident line for realistic operating conditions. So for example, 73 degrees Fahrenheit as its base to predict that behavior over the long-term stress. And so the mathematical confidence of that trend line, we can develop a hydrostatic design basis for each of the resins. And so we apply a design factor to that HDB that bridges the differences between lab conditions and real life. So that means resin and pipe manufacturing, shipping, handling, storage, installation conditions, temperature fluctuations, sky's the limit. So as I stated, these documents are about building confidence in HDPE. So the end goal of that TR3 evaluation is to allow the industry to define this pressure rating for verified resins. And that's going to give you that full confidence beyond that conventional service life expectation. So once those testings are completed and established HDBs are produced, manufacturers then get a TR4 listing, either a dependent listing or an independent listing. And that TR4 listing is like that verified check mark that you'll see on social media platforms. It's just kind of an indicator that the products that we're describing have met all the requirements of TR3, their data was valid, and the end user has that confidence that this material can handle the operating pressures that are rated for. So TR4 is definitely the more practical bit when you're writing a pipe specification. So this is where MB03 comes in. So MAB stands for Municipal Advisory Board, which is a group within PPI that's made up of utilities, consultants, contractors, and researchers that are experts in the HDPE industry. They've developed good technical documents. The first is this model spec. So a good model spec is essential to specifying information about HDPE pipe correctly. I frequently see old specs come across my desk that still refer to PE 3408s. They still refer to outdated standards like the ASTM D1248, which I think was changed to not include PE piping like back in 2000. So referring to, there'll also be examples that'll be like referring to different piping materials like PVC, but they've just changed the word PVC to HDPE. And so that's kind of an example of what we don't want to do when we're specifying our pipe products. A good spec is going to be accurate, it's going to be up to date, and it's going to be helpful for your whole life cycle. So if you want to receive and use a product that meets the standards of the current industry practices, you have to specify the right information. So a good specification can be utilized in all stages of the product's life cycle. That means you're going to use it in design, procurement for construction itself, maintenance, repair, future expansions. So I look at the MB03 because it lays out a good expectation for sizing and DR that gives you valid information for those, pressure class, surge allowances, even max test pressures that you'll see. In the materials portion, we'll go we're about to come full circle on the first two TRs that we discussed. So basically the spec indicates the right material for the job. That's going to be PE 4710. It's going to have a cell class of 44, 55, 74C. Now you don't need to memorize that whole bit, but just know that each digit of those cell classes represent a range of material properties that make a resin suitable for pipe. And so what safeguards are we going to have to make sure that we're getting those resins? We're going to do what we said before. We're going to look at those dependent listings in PPI TR4.
So
Additionally,
Matt,
yeah,
could I ask you a question on that slide? You know, I get asked all the time, you know, what do the standards say for what DR should I be using in water systems? And, you know, I say, well, there really isn't a standard, there's a practice. And here you've listed DRs 9 through 17 on that slide. What do you see for the most common used, and what should people be using for their water system?
yeah. I mean, I would say that if it's a gravity fed system, you know, you've got your 100-foot water tower driving it, you're probably going to see DR17, DR11 fit the bill just fine. It really does depend on the pressure, you know, for the application, but those seem to go pretty well.
Well, I see, you know, one of the leaders of our industry, Harvey Svetlik, has said for years, you know, if you only need a DR17, just use a DR17. But engineers, being who they are and the way they like to design, they're going to want to use a thicker wall pipe. So I tend to see an 11 more often than anything else, regardless of the method of installation. Sometimes if it's a really large diameter and a big drill, they're going to use a 9. But even though it's not a standard, I'd say the practice is probably an 11, much to Harvey's chagrin.
Right, right. And well, and to that point, I would say that, you know, we tend to go conservative because we want to limit the risk that we're putting into the operation. But it puts us in an unfair light when you're comparing against other competing materials, because if you can use a 17 and you're quoting a DR11 against a DR18 PVC, you might be just running up the cost for polyethylene for no reason. So I really like to look for a reason to do the math, so to speak.
Yeah. Hey, Matt, if I could jump in there real quick. I mean, I think Peter hit on a good point that, you know, he was talking about the drill and all that kind of stuff. So yeah, DR11 is, I think, the default for HDD applications for a
Right.
number of reasons. It's a tough product. You can do a lot with it. It takes a lot of rigor of those applications. And you can just, like I said, you can just do a lot with it, and it takes a lot off your plate that you got to deal with. But like you said, on an everyday basis, if you're just laying pipe in the trench, DR13.5, DR17 will work as far as a 100-year design life. So really, it's the installation method. It's what you're looking to do, what you want to take into account, what you don't want to take into account, how much margin of safety you really want to put in on your system. And, you know, as you start adding on those layers, it adds on potential costs. So everything is a balance. So while DR11 seems to fit the bill a lot of areas, there's no reason why a thinner wall pipe wouldn't suit just fine.
Precisely. Additionally, so the MAB, it also says you should follow AWWA, C906 or C901, depending on the size, which those are going to dictate frequencies of tolerances and of various measurements and physical tests for the pipe. So it basically is prescribing the quality level of the pipe.
Yeah, real quick. So you mentioned that. I just wanted to jump in there. So for C901, that's a good point you made in differentiating the distribution sizes and transmission sizes versus the service sizes. So C901 being mostly service sizes, 1/2 inch to 3 inch, that standard was revised last year or maybe 2 years ago now. And it is recommending DR9 for all service line sizes. And there's a reason for that. Service lines actually are the hardest product to put in the ground, to be honest. The less cover, less care is put into installing them. The most demand is placed on them. So going to a DR9 gives you a lot more toughness, a lot more robustness of that product. to give you that 100-year design life in all applications. So that's kind of why it's become the default for those sizes going forward.
Very good. So also having information on installation conditions can be helpful when you're making that leap from design to construction. So MB03 gives examples for, all manner of pulling applications, because this can be one of the most critical loads that the pipe's going to see in its whole life cycle. So you want to put those safe stresses that you can handle. And then additionally, it makes references to the other applications that you may see pull-ins used for: HDD, slip lining, pipe bursting. So that concludes the specification section. So I'm gonna pass it to Stephen to start the dive into design resources.
Hey, before we make that transition,
sure.
I'm going to interrupt you guys for just a moment. We're going to launch a quick poll here. So everybody out in the audience, please just take a moment and give us your opinion on this question. We love collecting data when we have a good experienced group like we have today. So which of the following benefits of HDPE use do you find most compelling? We'll leave this up here for about a minute. These are the typical benefits we tout everywhere in North America, and just want to get a little bit of data on what our engineers on the call today find most compelling. We'll give this about 10 more seconds. We've got more than half the group responding so far. And that's just about everybody. I'm going to go ahead and end it. And looks like flexibility and leak-free went out. Leak-free is what I personally find most compelling, and I bet a lot of that depends on where you are in the country and what it's like to source water. So thank you for the info, Matt and Stephen. I'm going to turn it back over to you guys.
Great, Drew, thanks. So as we transition more into the design phase, so I think one of the major design tools out there, aside from the PPI handbook of PE pipe, which is a good resource, but AWWA M55 PE pipe design and installation manual has just been revised. So it was just published last fall. It's available from AWWA by PDF or in print. I recommend, if you're going to be doing some municipal work using polyethylene pipe, this is a very valuable resource. 11 chapters. Like I said, it's fully updated with all PE 4710 design criteria, all the engineering properties associated with PE 4710. So you can take full advantage of everything that this material can bring. Chapter 4 talks about working pressures, the derivative, how you derive pressure class. And remember, every material defines and derives pressure class a little differently. So pressure class is not pressure class is not pressure class. Each one means different thing depending on the material it's meant to go with. So you got to remember that. And chapter 4 gives you a good explanation, as well as the surge allowance that polyethylene has. Because it is unique in that, because of its combination of toughness and ductility, it can handle these surge events. So much higher surge events with changes in velocity can be handled in polyethylene because its modulus is lower. So that change in water column velocity doesn't translate into the same percentage of increase in pressure. So while you can still handle 1.5 times the working pressure on a recurring basis, now that's multiple times, dozens of times a day for 100 years, or even 2 times the pressure class rating on occasional. So once a day, once a month, something like that. So there's a lot of robustness and capability built into that to take advantage of. The other thing, chapter 5 is a great tool. This was just fully rewritten and revised by Amster Howard. He used to be with the Bureau of Reclamation. He says he's retired, but I think he's doing more now than he ever did at the Bureau. If you've ever met the guy, he just lives and breathes this stuff. He's like the guru of soil design, as you guys, this flexible soil theory. His goal is to get all of these manuals using the same terminology, same test methods for compaction, all of these things that make sense. So we're all looking at it and talking about the same things. And I believe this is the first chapter of the AWWA design manuals that has taken this lead. So you get a lot of good information from that. It shows you where polyethylene doesn't really need to be engineered design for burial. If you're in a certain range, certain soil depth, certain water table, certain DRs, you really don't need to do anything else with it. You can just throw it in the ditch, a mild compaction around it, and you don't have to worry about soil overloads and things like that. Now, if you have certain situations, it's under pavement, certain live loads, then you might want to go through and do unique design, which steps you through all of that. Chapter 6, joining and fittings, it gives you a great in-depth information on that. And Chapter 8 on the installation portion. Chapter 10 on maintenance and repairs, which is a very key part and a new part of this manual, because once you get it in the ground, you got to know how to take care of it. And this gives you a lot of information in that area. It's also chock full of different appendices. So just an example, Appendix B here deals with earthquake applications. It's not always something that every part of the country needs to worry about, but what it does give you is the ability that polyethylene inherently has in it for a fully fused ductile system. You get the earthquake resilience of an earthquake design system without having to do anything additional. It comes with the polyethylene pipe that you're already buying. And that's been proven by decades of use in high earthquake areas where polyethylene piping systems have survived incredibly well, much better than any other ones. Hey, Matt, you got something?
No, I was taking over. If
Taking
you're
over
done.
the next one. Okay, yeah, I'm kind of going on a little bit, but that's a real key aspect of this manual, and you get good, current, up-to-date information. And it's not just earthquake areas. Anywhere you have soil movements, soil subsidence, floods, droughts, hurricanes, anywhere you might get something like that going on, you also need that same type of strain and stress capability that polyethylene brings to it. So I highly recommend getting the manual for that. Thanks.
Okay.
Back to you, Matt.
All right. So the next design document is the PPI permeation report, or more specifically titled Assessment and Calculation of BTEX Permeation through HDPE Water Pipe. So this document, it details everything about BTEX, which is benzene, toluene, ethylbenzene, and xylene, and how it permeates the pipe material. So its effects on, it also goes into its effects on health and the EPA maximum concentration limits, or MCLs. And this is an important evaluation because it's a common concern that's raised in municipalities or industrial districts. And misinformation can be used to attempt to paint HDPE pipe as a poor choice in just simply in those conditions because the soil's contaminated. And so the first thing to point out, it's BTEX is soil contamination is a concern for most piping systems, not just PE. While hydrocarbons can permeate PE, they can also permeate gasketed joints, the elastomers that are used for PVC or ductile iron connections. So specifically for HDPE, this document helps calculate the estimated BTEX permeation for the end user to determine whether or not it'll be above or below that EPA MCL limit. Alan, you got something?
Absolutely. So for civil engineers that are on the call, what we're really looking at is known brownfields in developed areas. If there's a pollution plume contamination somewhere, we typically don't put anything in there. You fix the problem either through environmental cleaning processes or what have you, but you typically try to avoid putting any type of a pipe there. One of the misconceptions about polyethylene is that the hydrocarbons do actually move across the polyethylene itself, and the reason why is because the molecules of the high density polyethylene pipe and the way that that happens. So in gas industries, they've looked at this problem for some time already, and it denigrates the pipe structurally, but there's equations that define that for us when we know what that pollution plume is, and it doesn't dramatically shorten the life. We just look at the PSI operating pressure as it goes through there. But generally, for known pollution areas, we're going to put back a double system for HDPE if it's got to go there. So if you're putting a different type of pipe material type as well, you have to put in a gasket that actually is more expensive, that precludes any type of hydrocarbon permeation through that, as it will permeate through it. But as a general principle, we try to solve those brownfield problems if we can, or don't put pipe there. But a dual wall containment unit also would help pretty dramatically. Landfills throughout the country use dual wall containment for leachate moving around in landfills itself too. So, that's just
that dual wall is something that Monty can fabricate, Alan. So you and I worked on a project last month where the owner had an issue with routing it because he couldn't get around it. So he wanted to go through it. So we said, okay, but just dual contain it. So a distributor fabricated those spool pieces for him.
Yep. Pretty standard process. Go ahead, Matt, come back on, and sorry to interrupt there. Thank you.
No, not at all. That's very useful information. All right. So the report also includes that table of the EPA national drinking water regulations for BTEX. And as you can see, the allowable levels are pretty low. They range from 0 to 10 micrograms per liter, based on which component of the contaminant we're talking about. But this definitely illustrates how real the threat is if allowed to get to your drinking water. So the report developed a simple flow chart that helps guide engineers in those evaluations. So we go from knowing X levels of hydrocarbon in the soil around the pipe and you're able to calculate how much ends up in the drinking water. So first we consider groundwater. So BTEX itself is highly soluble. So permeation is going to be facilitated more readily when the pipe is below the groundwater table than it would be if it's above it. So also the permeation rates for the different contaminants will pose a different level of risk depending on those conditions. And so after that, we consider whether or not the pipe water is flowing, because if it's stagnant, that means you've got a longer period of time for permeation to occur that'll raise that standing water's concentration of BTEX. So you do that, then you apply pipe thickness, ground temperature, and soil type factors. And the resulting is that estimation that'll end up in your pipe water. But many of these situations end up resulting in a negligible contamination or an allowable contamination. But the only way to know is to run the numbers. And that's why this is a necessary evaluation. And thank goodness for this resource to allow us to evaluate that. For the last resource in our design section, I'd like to plug the PE Alliance engineering package. I think it's important to place here because not only does it contain nearly every piece of literature that we're discussing today, but it also includes the Alliance for PE Pipes standard details. And this document has the standard details are a bunch of engineering details for connections using PE pipe. So there's about 20 of them, I think. They're all engineering drawings showing connections for common elements like connecting to fire hydrants, tapping service lines, going into manholes. It also shows the differences between connections using fusion or non-fusion methods like mechanical couplings. So now we're going to get back to Stephen to start our installation portion.
Yeah, thanks, Matt.
Not a problem.
So another very handy guide that comes out from the Plastics Pipe Institute is the PPI Material Handling Guide. So if you're not used to how to handle polyethylene pipe, This is a great resource. It goes through a lot of different aspects of putting the pipe on a truck, trucking it down to a job site, taking it off the truck, what to do with it when it's on the job site, how to move it around, and how to handle it safely. So there's a lot of just key things that you wouldn't normally think about. This version was published in 2018, but this guide's been around for a number of years and has gone through, gosh, I don't know how many permutations, probably a dozen different revisions over the years, and just gotten more detailed and more information to it. So the whole idea around it is safety. How do you do things safely with it? So the different types of equipment that you should use to move polyethylene around. Unloading is just as important. You have to have the right tools and the right equipment on the job site. We're going to see here in a minute, kind of example of what you do, and more importantly, what you don't do. Also, how do you inspect the product once it gets on the job site? How do you know you got what you wanted? There's some tools for that. Proper storage on the job site, and even cutting polyethylene pipe. You'd think, well, it's plastic, it cuts pretty easy, but you got to be careful. It can melt if you're not careful. You can get a backlash from chainsaws. You should never stand the pipe or the stick straight up and cut it partially and let it fall and break off. A lot of different things to take into account. But I want to talk about loading. So here would be an example of how you might want to move a piece of polyethylene pipe around. The key parts here to take away is that, you're using nylon straps that are good, safe, working condition, not frayed or torn anywhere. They won't damage the product. You can pick it up from the bottom or from the top, depending on the type of equipment you have, and move around safely. The next slide would be a video. If you could play that. This is how you don't want to unload polyethylene. Take great care and line it up, and use that bucket. I'm not sure how to that bucket, but we're going to see here in a minute what not. Thinking about it. He's going for it. And there we go. That's how you don't want to unload polyethylene pipe. So you don't just knock it off the truck. Yeah, it's light. Yes, it's plastic. Yes, it's very, very tough and durable, but that's not what you want to do on the job site. I mentioned earlier about a incoming inspection form. Now, as part of the HDPE app, as well as in the material handling guide, you can go and download this form. And what it just kind of goes through the details of things you might want to take into account when your load of pipe arrives on the job site. Just what job it is, who is a manufacturer, what specification was the product made to. All this is found on the print line. The print line has all the information that you'll need on that. When was it produced? What material was it produced out of? P4710. What's the OD? What's the DR? Make sure all those match. Make sure it's not damaged. Make sure it's strapped properly. You can check dimensions if you want to do that. I encourage anybody that has the tools to do it to do that when your equipment comes or your pipe comes out there. But remember, taking dimensions of pipe isn't always as easy as you think. You can't just put a tape measure on there and measure OD accurately. You might want to use a circumferential pie tape, which is what we always use in the manufacturing industry. And you want to use a micrometer to measure wall, but a ball micrometer and not a flat anvil micrometer. Just certain ways to do it to make sure you're getting what you really need. It's a good resource for that. Next. Also, if you're taking pipe off the truck and say it's maybe unbanded or you're breaking apart bundles, how high can I stack it? It's a very common question. Well, it depends on the size of the pipe, of course. So the smaller the pipe, you can stack it higher. If you get to thinner DRs, then you want to not stack it quite so high. Again, this is something you need to do safely and make sure that the pipe is protected and is not going to be damaged or ovalized in any way. So again, just a good rule of thumb for that.
So Stephen, speaking of stacking, I had an engineer from Bend, Oregon come to one of our events, and she was kind of upset about polyethylene, and I can understand why. So she was doing her first project with poly, and it was like a 24-inch, and it was a hot summer day, and it was a cool morning, and she got a call from the police department saying that her polyethylene pipe was walking down the highway, and it was unbanded on the top of a stack on site, getting ready to start the project, and it heated up during the day.
Yeah, it can do that. So you do have to watch thermal effects. So, you know, in the heat of the day when the sun's shining on it, especially let's say the temperature changes 50 degrees or even 40 degrees, and then the sun's shining on it, can be in another 10 or 20 degrees on top of that. The sun goes across, it'll shine on one side and make it bow one direction. As it comes across the other way, it'll even change and start bowing the other direction. So it can move a little bit. Not common, but it is potential. So it is something that you may want to take into account if you have loose sticks laying around.
Yeah, so Stephen, one of the things I like to point out on this chart, it's kind of counterintuitive to what you may think. You know, people see like a thinner pipe wall and they'll think, oh, okay, I can't stack that one as high as a thicker pipe wall. And the opposite is actually true. The thicker the pipe wall, the heavier the pipe. That means every layer on top is going to be heavier than if it were a thinner pipe wall. So that's something to point out about this chart. And I find it useful for people in the field to be aware
Well,
of.
what does above DR17 mean? Does that mean a DR21 or a DR11?
Right. That is a thinner pipe wall. So the thinner the pipe wall, the higher you can stack.
Okay, so
That would be a DR21 would be
It'd be a
above.
DR21.
okay, so the column on the right is DR11, column on the left is 17 and above,
Correct.
or above 17.
Above 17.
Yeah, okay, thank you.
Good point, Matt. Next slide. So is this? So other part is the fusion process. So a unique characteristic of polyethylene pipe is the way that it can be heat fused together using hot plate technology. So PPI TN51 kind of walks through the whole butt fusion process. If you're going to butt two ends of polyethylene pipe together and fuse them, we don't typically call them welding here in North America. We call it fusion because that is really what's happening. So TN51 is just a good summary. It's not, doesn't give you the methodology. That's going to be an ASTM F2620 is the procedure to do a butt fusion and a socket fusion. But this document will just walk you through what is the process? What's a fusion structure look like? What's the terminology that I need to get used to? How's it actually working? So you can see the history of it and how it comes together. Next slide. And so here's a quick little video of actually butt fusing a piece of pipe together. It happened very quickly. Let's play it one more time, Matt. The heated ends come together. Now those have been heated to 450 degrees Fahrenheit, brought together on a controlled manner with a controlled interfacial pressure to give you that nice rollback bead. And then it cools and you get the what they call the co-crystallization of the material that gives you a true interface that's just as strong as the pipe. That's the key. Other types of plastic you might be able to fuse, but just because it looks like this, it's not the same. The material is behaving differently. With polyethylene, you actually get interfacial cross mixing of the molecules, which give you those tie layers that hold it together and make the joint just as strong. So here's an enhanced view of a butt fusion as to what it looks like on the wall. This has been heat treated to show you, just where the interface occurs. And the picture on the right is really unique. I mean, just to get a piece of pipe with that many layers in it, first of all, is a challenge. But then you can truly see the flow profiles and how the two pipe walls come together, and then as they're brought out in a molten phase, and then they extrude out the sides into the rollback beads. You can just see how the material flows and joins to itself. and why it actually becomes a strong part of the pipe and will not be the weak link at that point. Again, you get that co-crystallization. This diagram's a little bit more in depth on exactly what's going on and some of the terminology. We'll call it a melt flow zone. In steel pipe, you might call it a heat affected zone. While they might look similar, they're really not similar. A heat affected zone in steel and metal pipe is a totally different thing than what we're calling the melt flow zone in polyethylene pipe. But it is a part that where the melt has been enhanced and has come together and has flown in a different pattern in a different direction than the longitudinal portion of the pipe itself. So a good diagram if you want to see exactly what's going on and why it's a good sturdy joint, this is a good place to go. The other type of fusion is what we call electrofusion. That's where it doesn't take an external heating plate to apply the heat that melts the product. It actually has a coupling or a fitting with wires that are molded into it. Electricity is ran through these wires to heat them up in a very controlled manner. That in turn heats up the polyethylene pipe and the fitting itself, which is made out of the same polyethylene material. And then the interfacial pressure that's created joins those two pieces together in a very strong joint. So the Municipal Advisory Board of the Plastic Pipe Institute actually put these two procedures together to give the municipal engineer better direct information and how they would likely use it in their application. So there's two of them. There's 12-inch and smaller, which is MAB1, and there's 14-inch and larger, up to 30-inch, MAB2. The methodologies are the same. I mean, what's going on is the same, but what you need to do as far as the prep work and paying attention to certain things changes as you go into larger diameter pipe. So that's why they have two different manuals for that. I highly recommend taking a look at that. As you go to the next slide, you'll kind of see the general process. They all kind of work very similar no matter what size pipe you have. You want to cut the ends nice and square. You want to clean it with water or a damp cloth, first of all, to get a majority of the dirt off. You want to measure the stab depth that the coupling needs to go into and mark that on the pipe. And then the real critical part comes into play. So you're going to peel the outer surface of that off. So there's special tools. We used to just use scraping tools. The industry is moving now towards peeling. So you're peeling the first few thousandths of a layer off to give you an extremely clean virgin surface, if you will, that's free of any contaminants. And then it's important to keep that clean all through the process. If you're ever going to use any cloth to wipe it down, it has to be a clean, lint-free cloth. If you're going to use any type of solvents, it has to be a very pure ethanol of some sort. Isopropyl alcohol will work as long as it's clean and fairly pure. You just want to make sure you're not introducing any kind of oils or anything like that into the process. Once you get your coupling centered on there, you apply the heating electrodes to it. The control box, then you push the button on the control box. It reads the type of coupler you have if you're using a universal control box, and it will apply the direct amount of current into those wires to get the right heat for the right amount of time. It monitors that, turns it off, you let it cool, and you're good to go. But there are some processes if you're going to use clamps, rerounding clamps, to secure it and keep it in alignment on smaller diameter and even larger diameter. You want to make sure that pipe's nice and round with different clamping devices and rerounding devices to make sure you get a good joint all the way around, a good coupling.
All right. And so for the next document, we're going to talk about PPI's TN38 on flange bolting. So it's a subject that I think a lot of people get confused about with PE, simply because PE flanges, they can be self-gasketing. So that means that they can be used to seat against the opposing flange for a seal rather than having to use a gasket. That applies to materials that are harder than polyethylene or also to other HDPE pipes. So this document gives a pretty good breakdown on that self-gasketing method, but then it also gives you guidance on when gaskets are necessary and info about specifying the right gasket. So the technical note, it shows a logical breakdown that your total seating force, or sealing force rather, needs to overcome the sum of all the potential forces seen at that joint. So stacking forces can include pressurization, surge pressure forces, thermal contraction, bending forces, the alignment allowances, dimensional and material variance, and so on. So to simplify that stack up of forces, you can use the estimated equation for minimum operating bolt load, which is 7 times the working pressure rating times the ID area. So that cross-sectional area from the ID. Similarly, the design seating stress for HDPE, in order to obtain like a 2 to 3% strain, which will generate enough sealing pressure, is between like 1200 and 1800 PSI. So by comparing the two numbers, the MOBL and the MSF, the mean sealing force, you take the highest of the two divided by the number of bolts, and that'll be the force that you'll be generating, and you can measure you can calculate the bolt torque necessary to achieve that. Oh, sorry, I didn't show the last little bit there. So the technical note also shows the proper bolt torquing pattern. So for example, the torque values for standard size flange adapters connecting to common flange types. But the key driving the uniform loading is loading up the bolts in stages. And so that's doing that star pattern in order to, and loading it in stages in order to provide that uniform load and account for the stress relaxation within the fittings itself. So sometimes it takes additional torque attempts to achieve a suitable seal. Also, for larger pipe sizes, it's suggested to reduce that incremental torque value from 30% for each series of torques to 25%. That way you give this larger pipe a little bit more time to go through its stress relaxation. And again, you can end up having to do this again after 24 hours of wait to accommodate that in order to achieve a full seal. Now, there isn't a currently released standalone resource for these other methods of joining PE pipe. TN45 is currently under revision. However, the PPI handbook of PE pipe chapter 9 has a decent rundown on the different types of mechanical connections. And so looking here, you can see the different types: mechanical compression fittings. Basically, they create a compressive load on the pipe itself in order to seal. And that can be either through a threaded activation or a stab fitting. So looking at this group of, what is it? They're Plasson fittings. Essentially, you're doing a compression nut essentially over the fitting itself that activates that sealing force. For this Elster Perfection fitting, it's a stab fitting, so it's kind of finger trap like, whereas you apply the tubing end into the fitting, it gets trapped, and it also energizes some O-rings within there. For mechanical bolt type fittings, you've got to tighten these bolts, which the compression between these two plates actually is on an angle with an elastomer that actually squeezes the pipe surface itself. Or additionally, for this Romac type fitting, you tighten a couple bolts and it basically squeezes a seal to squeeze the outside of the pipe. There are adapters like the flange adapter and the mechanical joint adapter, such as these by Performance Pipe, where basically you're tightening up the flange face or you're tightening up the gland within the MJ itself. And then you also have the transition style fitting, where it's like a pre-manufactured fitting between the two pipe materials that you're going to bring together. And so you would just attach this end to the PVC pipe system that you're joining, and this end to another polyethylene through heat fusion or whatever method preferred. These tend to be the more stronger method because they're manufactured so that the pull-out resistance is greater than the pipe itself that you're joining. So now we're going to move on to the maintenance section. But before I change slides, I wanted to say that maintenance is a topic that we hope we don't ever have to talk about. That's because, and to clarify, polyethylene, when it's installed correctly, shouldn't need maintenance for years, decades, I don't know, centuries maybe. However, occasionally maintenance can be required because of third-party damage or improper fusion. And so while we can't control those third-party damages, we can control whether or not proper fusions are made. So that's kind of why I'm starting with this document, the PPI TN60, which is inspection of plastic pipes, fittings, and joints using NDT and NDE methods. So non-destructive tests and evaluations are things that can mostly be done in the field. So this document, while it goes into a lot of, or it doesn't go into a lot of detail of any particular method, it gives common methods to be aware of, which there's basic ones like bead inspection, hydrostatic leak testing that are very common. But it also briefly mentions new technologies that could shape how we do quality assurance in the future. Those may include microwave testing or ultrasonic testing, though none of these methods are currently standardized within the industry. So you're really relying on who's producing the method to come up with the means to guarantee that it's an accurate qualification. So one of the really best ways of doing an NTE or an NDT is by reviewing the fusion data during the fusion itself. And so there are tools, a data recorder that can track the fusion parameters, such as how long we stayed in each phase, the pressure applied by the machine, the temperatures during the test, to give a real-time record of whether or not we did those fusions properly. And so this video, it's going to be a really brief clip, shows in real time as that fusion machine operator is applying the pipe ends to the heater plate. And so you'll notice as it touches the heater plate, the recording tool is going to measure a pressure spike when the pipe touches the heater, and then it's going to reduce from the heat soak pressure, which is appropriate for this fusion. So just taking a look, and you can see on the monitor, the pressure spikes, and then it slowly relaxes into that heat soak period. And of course, this is all real time during the fusion and stored in a database, which means, and we'll just skip to the end here and jump to the next slide, that after that fusion is complete, you can review every single joint's data to see the beat up time, the heat soak pressure was achieved, the heater plate removal time, and the cooling time. And so any data that's outside the acceptable parameters can then be used to evaluate whether or not we need to cut out the joint and redo it, or whether or not there's some other practice that can allow for this joint to be kept in service. Maybe it's something that you can't take care of right away. So what tool, what a tool for evaluating this most critical control for a quality pipe installation. So now we're going to go back to Stephen to discuss what we can do when maintenance actually is needed.
Yeah, Matt. So you're right. I mean, we don't plan on maintenance, but it's always a idea that's out there, and there are solutions for it. So another interesting part and thing that you can take advantage of for polyethylene is its ability to squeeze off the pipe to stop flow. Of course, you can do that with other materials. You can get big hydraulic rams to squeeze steel pipe. The problem is it stays squeezed and doesn't come back. So you've kind of, that's a final phase or a final resort to stop flow in those situations. But for polyethylene, you can actually squeeze it flat, stop the flow, do a repair if you need to at a certain point, and then remove that squeeze, and the pipe will come back to its original shape undamaged. So that's a very unique feature that can be taken advantage of. The key is, though, it has to be done the right way. So this PPI document TN54 gives you the general guidelines of what you need to be looking for to do a proper squeeze off of polyethylene pipe for water, oil, and gas applications. This would be outside of, which might have a little bit different methodologies, but the same type of principle. So we're not going to play this video. So this is just to let you know that there are YouTube videos out there which show you how to do it. This is a typical manual handheld, maybe not handheld, manual squeeze off tool for smaller diameter pipe. As you get into larger diameter pipe, there's hydraulic assisted tools to do that. I think up through about 24-inch diameter is available. So there's the same way, though, these need to be qualified. So there's ASTM procedures to qualify the squeeze tool itself to make sure it's able to do the job it's supposed to do and not damage the pipe in the process. That's ASTM F1041. And then you also have, or excuse me, ASTM F1563 is it's all in this TN document from PPI. And then TN 1041 will give you information on the squeeze itself. So go to the next slide. This is an example. So I'm not supposed to read this table. I'll show you in a minute what it is, but essentially, there you go. So essentially what this is for the different sizes and DR pipe, it's going to tell you what is the squeeze time. And what that means is how long you should take to bring the two walls of the pipe together to complete the squeeze. Now, the guide will tell you no more than 2 inches per minute should that squeeze tool come down. So it's fairly slow. You squeeze the pipe off, it stops flow, you do your repair, and then you have to release that squeeze. Well, that's the most critical part of this whole process. And that's when damage can occur, is actually when you're releasing it and not giving the compressed material enough time to stretch and relax and not overcome its strain capacity at that point. So the rate of release of that squeeze tool is now a 1/2 inch per minute. So on 16-inch pipe, that can take up to 28 minutes. And so the first two columns, here you have the size of pipe. You have your size, you have DR starting on the left-hand side, DR 9, 11, and 17. And you have the
ID.
I believe that's the ID of the pipe. Yep, thanks, Matt. And then you have the squeeze times at different temperatures. If it's cold out, you have to do everything slower. So above 32 degrees, DR 17, 16-inch would be 7 minutes to squeeze the pipe. If it's below 32 degrees, then you have to take 14 minutes to do that squeeze. And you can see how the release rate is even longer. So in a cold environment, that can take as long as an hour to release that squeeze so you don't damage the product. It's a key benefit, but it's got to be done the right way. And this guide will give you a lot of information about where to go to get the right information on tools and the methodologies and how they're qualified. Alan?
Stephen, we had a good question for you. If you're using that squeeze off tool, are you supposed to be a certain distance away from a fusion joint, or does that matter, the location of the fusion joint?
It does matter. So that's a very good point. In the guide, if you take a look at, I believe it's ASTM F1041, it will give you all of those ranges that you should be away. So as a rule of thumb, typically 3 ODs of the pipe that you're working with, minimum, away from any fitting or fusion joint that you might have in the system. You don't want to do a squeeze any closer than that, because then you risk possibly damaging that joint or that fitting that you may be close to. So that's a really good question. But again, if you go to that standard guide for squeeze, ASTM F1050 or 1041, that'll give you the whole process. And those are actually in the process being revised in ASTM currently. And so it'll be the latest and greatest information there. So that's a really good point. Another good tool from the Municipal Advisory Board is MAB4. So basic HDPE repair options. There's a lot of different ways to do it. You don't always need to repair polyethylene, but when you do, you got to know there's methodologies out there. So what the MAB did is they took their very practical approach to what does a municipal engineer or a maintenance crew need to know in order to do these different types of repairs. And with polyethylene, there's lots of options. There's fusion options, there's squeeze off, there's put in a spool piece with electrofusion couplings or mechanical couplings or flange adapters. There's a lot of different ways to do it. So what's nice about this document is it walks you through in a flow chart type way and guides you towards the most practical or more, recommended type of fusion repair, or excuse me, damage repair type methodology. So you just kind of go through what type of a pipe do you have, what type of damage do you have, what do you have to work with, and it'll take you through this thought process and say, okay, I have this or I have that. And then once I get to the end, it'll tell me what's my best choice to use, whether it's mechanical coupling or a flange adapter or a combination of the two, or just electrofuse in a spool piece to give you a fully leak-free heat fuse system as well. So again, it's just a flow chart type process. So you don't have to be an expert in all these different types of fittings. It'll direct you towards which is the recommended path. So I guess just to summarize, Matt, if you want to come back on too, we have a lot of information out there. The Plastics Pipe Institute has been around for, gosh, I think going on 70 years now. So a long time. It's seen a lot of information. It's been gone through a lot of development of the plastic piping industry in general. And all the experts from that industry have joined in PPI to put this information together. And it's been generated over these decades to give you the most up-to-date and technically sound guidance that we have today.
Yeah, and I would just say that we're lucky to have such a wealth of resources, but being able to know that information exists, how to access it, and then being able to share it with customers, new employees, et cetera. We want people to continue to learn about this great product and then use it.
Yeah, great job, guys. Thank you for that. Monty, if you could come back on, how do our guests, Monty, how do they access these Hymax repair couplings and these George Fisher products to connect to other materials? And how do they access your techs? How do they access spool pieces or dual wall? Educate us on how to do that, Monty.
Right. Our website is www.secoronline.com. My email was in this package. The one correction, there's a dot between the M and the Harrop, m.harrop@secoronline.com. But there's a place in there to ask questions on the website or contact me directly. You can ask questions or request a quote, and we'll get into the project more with you and find out exactly what your needs are.
So Monty, did I get the email correct?
Yeah, on that one, on the other screen, that's correct on that screen.
Okay.
The screen was missing a dot.
Great. So that's how we get a hold of you. But I mean, how long does it take? I mean, if I wanted a 20-foot run, a dual wall 12-inch, and the design was good when I sent it to you, Monty, how long would it take you to do that?
To get the quote back and the research, well, we would get on it, as soon as possible. I think a lot of that just depends on the manufacturer's ability to produce it. But
Okay.
we will be immediately on it and see what we can do to help you.
All right. Well, thanks again for sponsoring today. And
Yeah, thank you,
Drew,
Peter.
please come on and say goodbye to our audience. Tell us when the next webinar, Roadshow Light, is going to be. And thank you again, Stephen, Monty, and Matt Hahn. Great job today.
Yeah, guys, thanks. That was a really good presentation. And to To our audience, thank you for being here today. 2 shows next week, Tuesday and Wednesday, just like this week. Standards on Tuesday, the Alliances Engineering Package on Wednesday. And a reminder, if you want that engineers package, shoot me an email, dmueller@pepipe.org. You can also respond to any email you got from Zoom over the last couple of days. Same if you have questions we didn't get to today, or if you need a certificate to show or prove that you were in attendance today. But with that, we are up against our time. Stephen, Matt, thank you guys for being here. And everybody out there, we will see you next week. Take care.
Pleasure.
Thanks, everybody. Have a good week.